In this example, we're asked to prove that for an ideal gas, u is a function of t only. In other words, u will not change with v or p as long as t is constant. Let's just spend a little bit of time describing this in mathematical terms. What this means is that if I represent u as a function of t and v, remember the Gibbs phase rule, we ought to be able to specify two variables, namely t and v, in order to fully specify the system. This would imply that du is equal to du dt at constant v dt plus du dv at constant t dt, dv, and this part would be 0, such that u can be determined only by changes in t. Likewise, if we want to express u as a function of t and p, then a similar analysis applies. Du is du dt at constant p dt plus du dp at constant t dp, and this would be 0. So we want to prove these things. Notice that this is equal to CV. By definition, it's the constant volume heat capacity. This, on the other hand, is not CP. CP is dH dt at constant P. Let's start with this. Let's use a fundamental property relation. We're going to start with du equals T ds minus P dV, and then we're going to divide through by dV and hold T constant. Du dV at constant T equals T ds dV at constant T minus P. dV over dV is 1. So what do we do with this? Well, there's a Maxwell relation that says that ds dV at constant T is equal to dP dt at constant V, which we can calculate from the ideal gas law. This would be dP is equal to RT over V dt, holding V constant, which would be R over V. And if we plug that in, plug R over V in for ds dV at constant T, we get RT over V minus P, but RT over V is equal to P. Therefore, we get P minus P, and we get 0. So that's half of our mission. Remember, we wanted to show that this is 0. The next thing we're going to do is show that this is 0. So now let's go back to representing, what I'll do is I'll go back to this fundamental property relation. And this time we're going to generate du dP at constant T. Divide through by dP. This will be T ds dP at constant T minus P dV dP at constant T. This is, by a Maxwell relation, equal to minus dV dt at constant P, which will be minus d by dt of RT over P at constant P. This is minus R over P, and this dV dP at constant T is d RT over P dP holding T constant. This will be minus RT over P squared. Okay, and let me adjust the positions a little bit so to make room. What I mean is this is equal to that, and that this is a separate thing. So when I plug in, what I get is that du dp at constant t is going to be minus r over p times t minus p times minus r t over p squared. This comes to minus RT over P plus RT over P, which is 0. So let me just box it to make clear that we've accomplished our mission. What we're saying here is that the ideal gas law tells us that U is exclusively a function of temperature, even if pressure and volume change. As long as temperature holds constant, then the internal energy of an ideal gas will not be affected. And that is what we wanted to prove.